And my presentation will be on intensification versus land expansion in sugarcane production. And I will, in fact, support my presentation with asking some questions. And also they will help me to guide the presentation that I will have till the end. So the first question is the increase in sugarcane production in Africa, is it from land expansion or is it from improving productivity? We already have seen Peter gave answer to this, but I will maybe still ask the same. And then the second question is, what is the potential for intensification on existing land? Is there any potential? The third question is, what is the implication of intensification on land use and water consumption? So to start from the background, also answering the first question, this is the sugarcane production in Africa. To the left is the FAO Stat 2005, showing only the production in Africa, and to the right is for 2012. Maybe if we zoom in, we could see it in a larger picture. And then here in the left, you see some countries even either they didn't report, or maybe there is no sugar cultivation. But then in the right, in 2012, there is areas which start to cultivate. And in fact, if you see both graphs, the country in Africa with the largest sugarcane coverage is in South Africa. But well, coming to the main question, there is expansion. In fact, just comparing these two, only these 2 years, 2005 versus 2012, and based on FAO stats data, there is an increase in land expansion by 13%, 13%. And in fact, it's also increasing as we speak. The second presenter already showed, also from the FAO stats, Peter showed that there is an increasing trend in production. However, the productivity, again comparing those 2 years from FAO stats data, is almost stable, or even showing on average decreasing. So on average from 61 ton per hectare per year to about 59 ton per hectare per year. Then answering our first question, so most of the production increase in Africa is coming from land expansion. It's not really from improving productivity. But then the question is there a scope for intensification? So most of the next presentation and up to conclusion will focus answering those things, and also showing how we could analyze towards answering this intensification question. So for that, I zoom in into one of the sugarcane producing country and also a scheme, which is called Sinavana in Mozambique. And I will focus only on about 10,000 hectares of that Sinavana sugarcane plantation. In fact, this name already have been appearing in our previous webinars, so it should be very famous name, Sinavana. And in this area, in fact, about three irrigation methods are predominant. That is sprinkler, furrow, and center pivot. So then the question is there a scope to intensify within this area, which is Sinavana? This area have almost the same agroclimatic zone. It means that the potential to increase with a climate limit is, it's comparable, and also it's possible. So what method and data I have used to answer those things? So data from vapor data. For those of you who maybe who just joined this webinar, Vapor is a FAO portal to monitor water productivity through open access of remotely sensed derived data. And then we used 3 layers of this vapor data land class classification, actual evapotranspiration, net primary production, and also we supplement this data with local information, which is more about crop season, as well as the scheme boundary and the agronomic parameters. And then we calculated the seasonal water consumption and production using those data. And next, we calculate the water and land productivity, followed by identifying what is the productivity target in that area, and then followed by assessing the productivity gaps. And eventually, then we showed how closing productivity gaps have implication to the production as well as implication to water consumption. In fact, this is supported with calculation equations, which I will explain here. So the biomass in the x-axis here is calculated with the equation explained here in the box. And in the y-axis, we have the biomass water productivity. And if we plot those variables per pixel for the whole Sinavana area, we see the orange clouds of pixels. And then from this, if we can we set a target? Definitely we could set a target, and in this case we defined it as a 95th percentile of both productivity, biomass as well as water productivity. And then here, where the two lines cross, is the productivity target. Then, once we have the productivity target, the gap was calculated by comparing this productivity target with a productivity at each pixel. So that gives us how much is the productivity gap. And eventually, we calculated the production projection as well as implication on water consumption. And here at the bottom of my slides, in fact, the whole activities in the green box are there, which will guide also what will be the result. So the next result is what is the land productivity. So the land productivity here plotted for 5 seasons from 2014-15 up to now. And all those bars showing the biomass ton per hectare per year. And the first 3 shows in the cluster the biomass at Sinavana for different irrigation technology, furrow, followed by center pivot, and then the whole scheme. And then the last column shows the yield of sugarcane for Mozambique, again from the Sinavana, from the FEO stats. In fact, the difference between those is not purely just it's a difference, but rather it's because the last one is talking or showing the yield, which it means after multiplying the biomass by harvest index. And also the difference is due to his report, that is the yield from the FAO stat for Mozambique is an average over the whole Mozambique area, which includes also rainfed. So this is the biomass, and as you could see, the variation is there across technology, even also the bar showing the standard deviation across space. So again, this land productivity across space, as you could see, it varies. So it varies from the smallest red, about 50 ton per hectare per year, to more than 100 ton per hectare per year. And also the graph in the right shows the distribution function of this biomass across the Sinavana. So it nicely shows the normal distribution, where also coloring the values which are above the 95th percentile, which we said they can be as a target or beyond those targets. So similarly, we plot for water productivity, and also this water productivity varies across space, and also the distribution also here shows the normal distribution. So with this, then can we identify the target? So to identify the target, we plot in the x-axis the biomass, and in the y-axis the biomass water productivity. And then, as I already showed, if we plot them, so if we plot them, then we can show, nicely the relationship between those two, and also the target productivity, which is indicated by the dark star. So from this, of course, those dark stars, and I mean those pointers or spots which have productivity more than the 95th percentile are indicated with the green color, and in fact, they are also spread across the whole space in Sinavana. So those spots could be considered for one season as the target, and then the productivity gap eventually could be calculated by considering the value of those targets versus the value at each pixel. So the productivity gap in the left is for biomass gap, in the right is the biomass water productivity gaps for 5 seasons, and also for each irrigation technologies. So as it is seen in this picture, the biomass gap is large under furrow irrigation compared to center pivot, for instance. Whereas the water productivity gap is very large or high under area irrigated by center pivot compared to area irrigated by furrow. So then, anyhow, having those gaps, then we calculated or we start to talk about what is by closing gaps. If we close those average gaps, what it implies. So we have this graph. In the X is again the biomass, in the Y-axis is the biomass water productivity, and it has now additional variable, which is the water consumption. Imagine this is water consumption per year. It's not even 12 months or 15 or 18 months. So we have the actual evapotranspiration in millimeter per year. And as you could see, all those pixels to the left, the reddish one, consume less compared to the dark green one. So by improving or closing productivity, we mean that either we move those pointers in the horizontal to the right, which is following arrow 1, then it means that is closing productivity gap, also then consuming more water. Also, it can be following pass 2, which means we follow this, since they have the same or almost equal evapotranspiration, it means it is possible to close the productivity gap without any implication to additional or without any implication to water consumption. And there is also a possibility following arrow 3, which is a vertical move, where it is possible even to save water while closing productivity. So then, if we close those productivity gaps, what is implication to the production? So the implication, well, this is already included, indicated per year, the average gap. So there is a possibility to harvest more than 100,000 of ton per hectare per year, ton per the scheme per year at Sinavana. And also this has, in fact, implication on water consumption, and it might consume about 13.4 millimeter cube, and also a possibility of saving about 1.4 millimeter cube. In fact, this saving doesn't mean that it is saving which could be reallocated for other area or for other sectors, because it's a moisture within the root zone, which can be also green water. But if it is a blue one, then there is a possibility even to save the water from the water withdrawal and to apply it. Imagine this water consumption, either additional or saving, is just only comparing the existing irrigation scheme. Because there is a possibility yet to increase the productivity, for instance, by consuming less water than what is indicated here. For instance, if we are applying mulching and other soil moisture conserving practices, interventions, of course, still the consumption are expected to be less and maybe the saving more. So this will take me to the final conclusion. So intensification at Sinavana by closing biomass gap can increase water productivity as well as production, and the production can be increased by more than 100,000 tons per year. This is in fact equivalent to producing from more than 1,000 hectares, or this implies even we are saving about 14% of the existing scheme if we are closing the productivity gap. But this comes with implication to water consumption, but this water consumption would be even higher if the production gain is coming from land expansion. So yeah, we are comparing this additional water consumption, but then I would expect to be less if I compare it, the yield is increased from the expansion. So subsequent studies could additionally consider, in fact, sucrose content rather than sugarcane, because this is also an indicator for, let's say, sugar production, which is the marketable product from sugarcane. And also it has to do with water shortage. Already Peter nicely said we could have the deficit irrigation. So it means it might have a positive implication to sucrose rather than just indicating there is a reduction into the biomass. So vapor plays an important role. In fact, we have seen this since the first webinar up to now, and it really bridges the data gaps, particularly the spatial details which are unavailable from the additional means of data collection, point data. The first presenter, Aberra Girma already showed they have just one data center to predict, operate, and to do everything. So in such kind of cases, also for future expansion or planning, vapor could really play a pivotal role. However, validation and accurate interpretation of results, diagnosis of the productivity gap, and formulation of practical solutions can be made if vapor analysis and results are complemented with observed data and local information. So yes, we have nice data, and also let us check it and let us also try to apply it. That's my final message, and thank you, and see you in the question and answer.